The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So now we're going to learn a few more operations about vectors. And these operations will be useful to us when we start trying to do a bit of geometry. So of course, you've all done some geometry, but we're going to see that geometry can be done using vectors. And actually, in many ways, it's the right language for that. And in particular, when we learn about functions, we really will want to use vectors more than maybe the other kind of geometry that you've seen before. I mean, of course, it's just a language in a way. I mean, we're just reformulating things that you have seen, you already know since childhood, but you'll see that the notation somehow helps to make it maybe more straightforward. So what is dot product? Well, dot product is a way of multiplying two vectors to get a number, a scalar. And well, let me start by giving you a definition in terms of components. So what we do, let's say that we have a vector A with components A1, A2, A3, a vector B with components B1, B2, B3. Well, we multiply the first component by the first component, the second by the second, the third by the third. If you have n components, you keep going, and you sum all of these together. Okay, and important, this is a scalar. Okay, you do not get a vector, you get a number. I know it sounds completely obvious from the definition here, but in the middle of action, when you're going to do complicated problems, it's sometimes easy to forget. So that's a definition. What is it good for? Why would we ever want to do that? That's kind of a strange operation. So probably to see what it's good for, I should first tell you what it does geometrically. Okay, so what does it do geometrically? Well, what you do when you multiply two vectors in this way, I claim the answer is equal to the length of A times the length of B times the cosine of the angle between them. So if I have my vector A, and if I have my vector B, and I have some angle between them, I multiply the length of A times the length of B times the cosine of that angle. So that looks like a very artificial operation. I mean, why would we want to do that complicated multiplication? Well, the basic answer is it tells us at the same time about lengths and about angles. And the extra bonus thing is that it's very easy to compute. If you have a component, see, that formula is actually pretty easy. So, okay, maybe I should first tell you, how do we get this from that? Because in math, one tries to justify everything to prove theorems. So if you want, that's a theorem. That's the first theorem in 1802. So how do we prove that theorem? How do we check that this is indeed correct using this definition? So, or in more common language, what does this geometric definition mean? Well, the first thing it means, before we multiply two vectors, let's start multiplying a vector with itself. That's probably easier. So if we multiply a vector A with itself using this dot product, so by the way, I should point out we put this dot here, that's why it's called a dot product. So what this tells us is we should get the same thing as multiplying the length of A with itself, so squared, times the cosine of the angle, but now the cosine of an angle of 0, cosine of 0, you all know is 1. Okay? So that's going to be length A squared. Well, does that stand a chance of being true? Well, let's see. If we do A dot A using this formula, we will get a1 squared plus a2 squared plus a3 squared, that is indeed the square of the length. So check. That works. Okay? Now, what about two different vectors? Can we understand what this says and how it relates to that? So let's say that I have two different vectors, A and B, and I want to try to understand what's going on. So my claim is that we are going to be able to understand the relation between this and that in terms of the law of cosines. So the law of cosines is something that tells you about the length of the third side in a triangle like this in terms of these two sides and the angle here. Okay, so the law of cosines, which hopefully you have seen before, says that, so let me give a name to this side. Let's call this side C, and as a vector, C is A minus B. It's minus B plus A. So it's getting a bit cluttered here. So the law of cosines says that the length of the third side in this triangle is equal to length A squared plus length B squared. Well, if I stopped here, that would be Pythagoras, but I don't have a right angle. So I have a third term, which is twice length A, length B, cosine theta. Okay? Has everyone seen this formula sometime? Yeah. No? I hear some yes, I hear some no's. Well, it's a fact about, I mean, you probably haven't seen it with vectors, but it's a fact about the side lengths in a triangle. And, well, I'm not sure that well, let's say if you haven't seen it before, then this is going to be a proof of the law of cosines, if you believe this. Otherwise, it's the other way around. So let's try to see how this relates to what I'm saying about the dot product. So I've been saying that length C squared, that's the same thing as C dot C. Okay? That we have checked. Now, C dot C, well, C is A minus B. So it's A minus B, dot product A minus B. What do we want to do in a situation like that? Well, we want to expand this into a sum of 4 terms. Are we allowed to do that? Well, you know, we have this dot product. It's a mysterious new operation. We don't really know. Well, the answer is yes, we can do it. You can check from this definition that it behaves in the usual way in terms of expanding, factoring, and so on. So I can write that as A dot A minus A dot B minus B dot A plus B dot B. Okay. So A dot A is length A squared. Let me jump ahead to the last term. B dot B is length B squared. And then these two terms, well, they're the same. You can check from the definition that A dot B or B dot A are the same thing. So there's no hidden trick here. This is really minus twice A dot B. Okay. So now let's compare these two formulas. Well, you see that this term is, I mean, this is the only difference between these two formulas for the length of C. So if you believe in the law of cosines, then it tells you that, yes, this is a proof that A dot B equals length A, length B, cosine theta. Or vice versa, if you've never seen the law of cosines, but you're willing to believe this, then this is the proof of the law of cosines. Okay, so the law of cosines or this interpretation are equivalent to each other. Okay, any questions? Yes?
Why isn't there cosine theta in the second one?
So in the second one, there isn't a cosine theta because I'm just expanding a dot product. Okay, so I'm just writing C equals A minus B, and then I'm expanding this algebraically, and then I get to an answer that has an A dot B. So then if I wanted to express that without a dot product, then I would have to introduce a cosine, and I would get the same as there. Okay? So yeah, if you want, the next step to recover the law of cosines would be to plug in this formula for A dot B, and then you would have a cosine.